Good morning everyone. So, in today's lecture I am going to talk about the numerical solutions of Euler-Lagrange equation. So far we have discussed about the various forms of Euler-Lagrange equation, and also we have found the solution to the Euler-Lagrange equation purely using analytical techniques. So, in today's lecture I am going to talk about what happens when we are stuck in a situation when the Euler-Lagrange equations are no longer solvable analytically. So, in that case we have the help of numerics, and I am going to discuss three different methods today in this lecture on how to solve, and later on in the course of this lecture I am also going to provide some other references for people interested in developing higher order numerics. So, the first method that we will talk about in this class today is regarding the Euler's finite difference method. So, this seems to be the simplest method that we can adopt in finding the solution of the Euler-Lagrange equations numerically, right. Let me abbreviate this method by EFDM. Okay. So, the basic idea of this method is as follows. The idea is we are going to approximate our function, or the function which involved in this functional optimization is the integrand, right. So, the integrand is what we have to approximate. So, we approximate the integrand and hence the integral into finite grid points, right. So, instead of now solving finding the optimum value, the optimum function of an integral, we are now going to find the optimum value of a summation. So, the integral in the functional changes to a summation over the particular set of grid points. So, then the next set of idea is then the moment we discretize our functional the integral into finite set of points, our integral becomes a summation, and then the problem reduces to the standard optimization problem. The problem reduces to the standard optimization case in multivariate calculus. So, the way we approach maximizing or minimizing a function in a regular vector space, that is the same way that we adopt in this strategy. And finally, the way to do it is, after we have discretized our functional, all we have to do is to find the optimal solution by setting the derivatives equal to 0, the derivatives with respect to the unknowns equal to 0. So, these 3 points reflect the basic idea of the numerical solution. Now, let me just build a little bit more background before I am going to highlight this methodology using some examples. So, then let me just say that we have a finite set of points. So, the way we numerically approximate our problem is that we use finite set of mesh points. So, use mesh points from x0 is less than x1 is less than x2 and so on, and the final set of mesh point is xn. This x0 could be the left hand side of the boundary and the xn could be the right hand side of the boundary. So, our integral is from a to b, and we approximate we approximate our derivative, our derivative y prime at grid points xi by delta yi by delta xi, right, which is also equal to yi plus 1 minus yi divided by delta xi, or xi minus 1 plus 1 minus xi. So, that is the Euler's forward difference approximation that we are using to approximate the derivatives at the points of our choice. And finally, the third rule involves we use the standard rectangle rule to change our integral into summation. So, use rectangle rule to change our integral f of y, which is integral from a to b of the function f of x y y prime dx, and we change it using into a summation which is as follows. So, I from 0 to n, well let me write this in the other page. So, the integral changes to a summation I from 0 to n, right. Well, it will be from n from 0 to n minus 1, because our function involves a quantity like yi plus 1. So, the summation involves I from 0 to n minus 1 f of xi, yi and derivative of y at xi, right, or let me say that this is approximated as delta yi delta xi, right. And then notice that we had an element dx. So, dx changes to delta xi, right. So, this is the function that now we have to maximize or minimize. Notice now the functional has changed into function, or let me call this as the vector function, which is a function of the unknowns y bar, right, or this is also equal to the function y0, y1 to yn, right. Okay. So, now we are going to treat, the idea is to treat the maximization of this function using the standard multivariate calculus. So, just a moment. So, before we do that, let us notice that this particular function has n plus 1 arguments, right. So, n plus 1 arguments. However, we have 2 arguments corresponding to the boundary condition. So, y0 and yn are the values of y at x0 and xn given by the corresponding boundary condition. So, there are n plus 1 unknown. So, we treat this function as a standard maximization or minimization problem, minimization of a function of n minus 1 variables, right. The 2 of the variables are just the boundary conditions, the remaining are the n minus 1 variables, right. And we find the solution to this problem by taking the derivative of f with respect to the unknowns. Well, f has multiple variables. So, let me call this as a partial. So, we take the partial of f with respect to yi from and set it equal to 0, where I is from 1 to n minus 1, right. So, this is the set of equations that we solve to find the necessary, or to find the extremum of this function. Okay. And further, let us assume that the grids are uniform. Assume uniform grid. Right now, we are going to make this assumption so as to simplify our calculations. So, assume uniform grid such that my delta xi is final point minus initial point divided by n, which is the number of grid points. Okay. I call this as delta x. So all that is required in this method is to just find the maximum of this function using the standard first derivative test. So, let us look at an example. Okay. So, the example says, let us go to the next slide. So, the example says that we need to find the extremal. So, extremize f of y, which is given by the integral from 0 to 1 half y prime square plus y square by 2 minus y dx. So, we need to extremize subject to the boundary condition y of 0 is 0 and y of 1 is also 0, right. So, my domain is x from 0 to 1. So, well, before I move ahead and solve this functional, find the extremum of this functional using the Euler's finite difference method, let us see what is the exact solution given by the Euler-Lagrange method, right. So, note that if we were to find the Euler-Lagrange equations, we are going to end up with the following ODE. So, the extremum y is given by the Euler-Lagrange equation, which reduces to this following ODE. So, students should check that by solving the Euler-Lagrange, we eventually get this following ODE. Okay. So, then the ODE has a constant coefficient ODE, which is non-homogeneous. The homogeneous solution to the ODE will be the solution to this equation, which means that we get that y homogeneous is a e to the power x plus b e to the power minus x, right. And the particular solution is given by y particular is equal to 1. We can plug and see that y particular equal to 1 satisfies the ODE. So, finally, the solution y of x is y homogeneous plus y particular, and the solution comes out to be a e to the power x plus b e to the power minus x plus 1. Okay. So, we have two unknowns a and b, and they can be found using these two boundary conditions. And let me just write down the final answer after finding the constants. I see that y is the following constants: e to the power minus 1 by e minus e to the power minus 1 times e to the power x plus 1 minus this quantity e to the power minus x plus 1. Okay. So, students should check that this indeed satisfies the boundary condition as well as both the boundary conditions. Okay. So, we already know the exact solution to this problem. So, now we are going to discretize our problem or our functional and see that the Euler-Lagrange method is well approximated by the Euler's finite difference method or not. Okay. So, let us look at what happens when we use the finite difference method, right. So, what happens is, let us, as shown in the previous slide, let us take a uniform grid. So, we take xi to be I by n, right. So, I take I from 0, 1 up to n minus 1. So, we take I to be, these are my following grid points. So, start so I from 0, 1 to n. Okay. So, then so these are my grid points. Then we also take my boundary points y0 and yn, they are both 0 due to the boundary conditions given by this problem. And then we see that our uniform grid delta x is just 1 by n. The domain size, the domain length is 1. So, then further we can describe delta yi. So, delta yi is yi plus 1 minus yi, and delta and yi prime, which is the derivative of y at the point xi, is delta yi divided by delta x, and delta x is 1 by n. So, this reduces to n times yi plus 1 minus yi, right. And so, what we have is yi prime square, we need all these expressions in our problem, will be yi prime whole square. So, we just plug in the expression here, we get that this is equal to n square times yi plus 1 square minus 2 yi plus 1 plus yi square. So, we are ready to substitute all these values in our original functional. So, the Euler's finite difference method reduces to the following function. We see that my vector function is as follows. This is also equal to the summation I from 0 to n minus 1 of f of xi yi prime delta x. It is a uniform grid, and we see that this is also equal to plugging in all the values inside this integrand. From the problem, we see that this is also equal to I from 0 to n minus 1 n square by 2 yi plus 1 square minus 2 yi plus 1 plus yi plus 1, well, yi square, right. And then the rest of the terms are plus yi square by 2 minus yi times delta x. Okay. So, then this becomes, so delta x is nothing but 1 over n. So, then I can simplify this expression a little bit more. This is summation of n by 2 I from 0 to n minus 1 times this quantity inside the bracket plus yi square by 2 minus yi divided by n. So, now we have a function, a vector function of n variables y0, well, n minus 1 variable y1 to yn minus 1, right. So, what we can do is we can further include the two unknowns coming from the boundary, that is y0 and yn, and set up the function, the total function in the form of in another form. So, we include, so what I just said is the following. So, we are going to include the endpoints, the endpoint condition, mainly the endpoints are y0 and yn, they are already 0, we know that, and we use them as, we include them as a Lagrange condition. So, include the endpoint condition using Lagrange multiplier. So, students who have done standard multivariate calculus should be aware of the Lagrange multiplier method. If they are not, we are going to do a very brief revision very soon. So, using the Lagrange multiplier method, we write down the new vector function. So, my new vector function now is the original function f bar of y bar, which is I from 0 to n minus 1 n by 2 times yi plus 1 square minus 2 yi plus 1 plus yi square, right, plus yi square by 2 minus yi divided by n times, well, plus the additional conditions that we have included are y 0 and y n, and we have included those using these additional constants known as the Lagrange multiplier. Okay, so the next step to the solution involves we take the derivative of this vector function with respect to the unknowns and set them equal to 0. Right now, since we have included even y 0 and y n, we assume that they are unknown, but later on we are going to use the boundary condition to eliminate them. So, if we were to use the fact, if we were to assume that y 0 and y n are unknown, we now have n plus 1 unknowns. Well, in fact, n plus 3 unknowns including lambda 0 and lambda n, right. So, we set up our first derivatives. So, my first derivatives are as follows. Notice that when I is 0, we will have the following expressions for different values of I. So, this derivative is for I equal to 0, we get that this is also equal to the following. So, here I have straight away used in the expression of capital F, we have used the information coming from the boundary, and for I equal to 1 to n minus 1, that is all the interior points, the expression reduces to the following: n times 2 y I minus y I plus 1 minus y I minus 1 plus y I minus 1 by n. And finally, when I is equal to n, the other boundary point, we see that the expression reduces to n times y n minus y n plus 1. Well, there is no n plus 1 involved. So, n minus 1 plus lambda n. Okay. So, then as I just said, we have n plus 3 variables. We have n plus 3 variables, and those variables are from y 0 to y n and the constants lambda 0 and lambda n, right. And we have n plus 3 unknowns, n plus 3 equations. We can see that here we have n minus 1 and we have, so these give me n plus 1 equations, and we also have, so let me call this as the setup as star. So, we have star is giving us n plus 1 equations plus the fact that y 0 is 0 and y n is 0 coming from the boundary gives us the additional 2 equations to solve. So, the system is fully solvable, the number of unknowns are equal to the number of equations, and we should get a unique solution. Okay. So, then all I have to do is to set up the linear system. We set up the linear system, A x is equal to b, and we solve for the system that gives us the unknowns y i's, and those y i's we are the approximate solution to the extremal, and that is the end of the solution methodology. But just to highlight how this solution compares with our exact solution, I have done some numerical simulations, and I would like to compare how does it matches with the exact solution. So, in this case, so this is our example 1. So, if we were to plot the exact solution was shown in our previous slide. The exact solution looks like this, and if we take only 4 grid points, we see that 3 of them will be interior, there will be 2 which are on the boundary, and we get a very jagged type of an approximate solution, right. So, the approximate solution satisfies the value of the exact function only at 5 different points, including 2 at the boundary. However, if we do the same exercise comparing with the exact solution with, let us say, higher number of grid points, let us say n equal to 20, we see that the solution is much more smooth and closer to the exact solution, right. So, that has all been that is just what I am showing what we have got through the numerical output. Okay. So, the moral of the story here is, the finer the grid point, the closer is the Euler's finite difference solution to the exact solution, right. In fact, we will show now next that the Euler solution converges to the solution given by the Euler Lagrange equation in the limit delta x goes to 0, or in the limit that the number of grid points approaches infinity. Okay. So, what we are showing is the convergence of the Euler's finite difference method. Okay. So, let me just again state our function. Our vector function is as follows: summation I from 0 to n minus 1 of f of x I y I delta y I by delta x I, right, times delta x. Now, we want to differentiate, the Euler method differentiates this vector function with respect to y I. Notice that y I appears in this argument, and also y I appears in this argument because my delta y I is y I plus 1 minus y I, and also it appears in delta y I minus 1 because that is delta y I minus y I minus 1, right. So, y I appears, if we want to differentiate with respect to the variable y I for this function, it appears in 3 places, one in the second argument and twice in the third argument as follows, right. So, if we were to differentiate, so the Euler's finite difference method says that we differentiate this vector function with respect to the variable y I and set it equal to 0, right. And now, when we differentiate this function, we see that this is also equal to the derivative of f at y I, that is the second argument here. So, let me, so this is evaluated at x I y I delta y I by delta x I, right, and plus well, I have, what I have done is I have scaled out this constant delta x. So, delta x will not appear in any of our terms on the right hand side. So, then the other two terms are well, so delta x I, this is nothing but delta x. So, I get two more terms, 1 by delta x times the derivative of this quantity with respect to y I, that is also equal to del f del y I times of the argument x I minus 1 y I minus 1 comma delta y I minus 1 by delta x, or delta x I minus 1, which is delta x, right, and minus, because y I appears here with a minus. So, minus 1 by delta x del f del y I of x I y I comma delta y I by delta x, right. We see that this is also equal to, so let me just rearrange some of these terms. You see that this is del f del y I at these argument values minus 1 by delta x times, notice that I have taken minus 1 by delta x out. So, I see that this is also equal to del f del y I of x I y I delta y I by delta x minus del f del y I of x I minus 1 y I minus 1 delta y I minus 1 by delta x, right. So, let me just take this constant in the denominator, and that shows the result significantly. Notice now, notice this. So, let me now take the limit delta x goes to 0 on this right hand side, right. So, the right hand side involves this term as well as this whole term, and we see that in the limit delta x goes to 0, this quantity is nothing but the partial f partial y, and this particular quantity is nothing but negative of the ordinary derivative with respect to x of partial, well, this is nothing but well, there is a slight error here. So, we have that this is del f del y prime, right. So, we are differentiating with respect to the third argument here. So, this is del f del y prime, del f del y prime and del f del y prime, since we are differentiating with respect to the third argument which is y prime, right. So, then in the limit this becomes the regular derivative with respect to x of the partial f partial y prime, right, and on the left hand side this is already set equal to 0, and we see that this is nothing but the Euler Lagrange equation, right. So, what I have shown here is in the limit the Euler's finite difference method gives a solution which approaches the solution of the Euler Lagrange method. Okay.